Welcome to example number 1 and our quick discussion of Hooke's law. This should be a review because we've discussed Hooke's law, but let's just go over it. Hooke's law states that the restoring force F is directly proportional to the stretch distance x, or the displacement from equilibrium. And so you can see that there's this straight linear relationship here, and that the force is proportional to x. And if it follows this, ideally, then it's called Hooke's law. Now, not all things follow this, or there is a point where they reach a elastic limit and you do not have a direct relationship anymore. And when that does not occur anymore, then it doesn't obey Hooke's law. So this applies to simple harmonic motion because we're going to be studying one case which involves a spring and a mass attached to it, and the force that keeps it oscillating back and forth will be is the restoring force, and it's going to obey Hooke's law. So here we have a spring being pulled, and you can see the applied force. And as you stretch it or compress it a distance x, there's a force that either will try to bring it back towards the equilibrium, which is this spot right along here. So that's why it's called the restoring force. And that's why there's a negative sign here, because it's always trying to return it back to equilibrium. So that is, the restoring force is going to point in the opposite direction as the displacement. So if you pull it to the right, that's your applied force, but the spring will apply a force backwards, returning it back to equilibrium equal to the force that you pulled it to the right. The units of the force is newtons, but just as an aside, K is known as the spring constant, sometimes called the force constant as well. And this has units of newtons per meter typically. So let's take a look at example number 1. We have a tire here in the tire valve, and we're checking the pressure. Now, a basic version of finding your pressure would be a little, looks like a pen, and I'll probably show one in class here. And it's just basically has a little spring inside, and so when the air pushes down here, the spring is calibrated with a little scale here that will tell you exactly what the pressure is. So what do we know in this problem? We know that the spring constant is 320 newtons per meter, and we're told that the bar has an extended displacement of 2 centimeters, which we'll need to convert to meters, so 0.02 meters. And we're asked to find two things. We're asked to find how much force was applied by the air, and then also what is the work done. To find the force, we're going to use Hooke's law, so F equals kx. You'll notice now I'm not putting the negative in here because I'm just really finding the magnitude. So the negative is only really there to remind us that it's going to be in the opposite direction that you pull. So it shows what direction it is. So it's a spring constant of 320 newtons per meter multiplied by 0.02 meters, and that will give you a force of 6.4 newtons. To find the work done, we're going to have to be careful here. See, the force that you found here was the force when it reached the max amount. So you can imagine if you look at this picture here, let's say right over here, that would be a force of 6.4 newtons. But if you were to take the definition of work, which is force times displacement times cosine of theta, and take the 6.4 newtons and multiply by the displacement, which is 0.02 meters, you're going to find that you will not get the right answer, because you're simply taking the max amount of force and multiplying by the total displacement, but that force is actually zero at a distance of 0, say at 0.01. It would be about half of that, so it would be about 3.2 newtons. So really the force is directly proportional to the displacement, and you're not going to get the right answer if you assume that the force has been constant throughout the whole movement. So really this won't work. You'll have to really think of it as it's the area under the curve. So now you could plot this graph like shown up here and take the area of this triangle, or you could also realize that the work done is also a change in spring potential energy, which is calculated by using 1/2 kx squared. So that's 1/2 times the spring constant, which is 320 newtons per meter, multiplied by the displacement of 0.02 meters squared. And that will give you an answer of the work done being 0.064 joules. And that's it for our discussion of Hooke's law and example number 1.